what I was explaining last day. I'll provide a quick recap, and then we will see the DQN algorithm, and then we will move on to Monte Carlo tree search, which is a family of algorithms which is employed by AlphaZero. Okay, so recall that a Markov decision process is a tuple SIR row R, where S are the states. Some states are initial, some are final. The initial are S0 and final are SF. And we assume that there's just one initial state called S0. R is a set of rewards, A is a set of actions, and R is a map that specifies the reward you obtain after taking an action A at state S. And then rho is the dynamics of the model. It maps each state and action to a probability distribution over S. So the probability distribution assigned to SA is denoted like this in this conditional probability notation. And rho of S prime conditional on SA is the probability of moving to state S prime after taking action A at state S. Okay. And we use this notation X sim X to denote that X is sampled from a distribution X. Okay, a trajectory or an episode is a sequence of, you have some states and actions and rewards, and this reward is, R1 is the reward of taking action A1 at state S0, and S1 is a state where you move to after taking action A1 at state S0. So the S's are states, the A's are actions, Ri's are rewards. Ri plus 1 is the reward of taking this action at this state, and Si plus 1 is sampled from this distribution. And the episode starts at the initial state and it ends at some final state. The return of the trajectory is the sum of all rewards with these discount factors. The discount factor is some number that is very close to 1 usually. You can also think that it's just 1 for simplicity. Then a policy pi is a map from the state to a set of probability distributions over A. So it's kind of a set of rules of which action you should take at a given state. But it's stochastic. Again, we use this notation. Since it's a probability distribution, we use this notation resembling conditional probability. Pi as condition on pi A condition on S is the probability of selecting A if you follow policy pi when you are at state S. And again, we write A sampled from this probability distribution. Okay, well, this is just to remind the notation. So we are all on the same page for the next topics. We saw last week that a policy pi induces a distribution over the set of all trajectories. We denote it with this P. And the expected return of a policy pi is the expected return of trajectories when trajectories are sampled with the probability distribution induced by pi. So the weighted sum of the returns of trajectories weighted by the probability assigned to them. So it's just the average return of the policy. And the goal is to find a policy that maximizes this expected return. The policy that maximizes it is called optimal, and we denote it by pi star. Okay, And then we had the Bellman equations. Given a policy pi and a state S, the value, oh, we had this definition. So given a policy pi and a state S, the value of a state with respect to the policy is defined in this way, which is the expected return of an episode that starts at S. So it's the expected return if your initial state is S. Oops. And similarly, we have the value of a state action pair, SA, which is the expected return if the first state is S and the first action is A. And then we had these Bellman equations which relate the value and the Q values, so the values of states and the Q values of state and action pairs with the rest. It relates these values and Q values between them. The most important one is this one, but unfortunately it's invisible. But we will see it now again. Okay, so the Bellman equation gives us a method for quantifying how far a policy pi hat is from the optimal, how far a policy that we are working with is from an optimal policy. And we don't need to know anything about the optimal policy. Why is that? Because if our policy was indeed the optimal one, then we would have that the Bellman equation for our policy satisfies this equality, which is the equality. This is the Bellman equation for the optimal policy. So this is the Bellman equation for any policy, and this is the Bellman equation you obtain if you replace pi by pi star, the optimal one. So it's just this expectation, and in here, instead of an expectation, you have a maximum among actions. So if your policy pi is indeed the optimal policy pi star, then you have this equality. Equality here. However, our policy pi hat is most likely not exactly equal to pi star. So these two numbers won't be the same, because it's unlikely that just by we are just trying to find the optimal policy, we haven't found it yet. So this thing and this thing will not always be the same. So the difference, how far these two values are, allows us to quantify how far our policy is from the optimal one. So the closer pi hat is to pi star, the smaller the following value is. And this is just the square error of this value and this value between these two values. Okay, which I denote LSA of pi hat. Okay, so this means that to find a policy that is close to optimal, it suffices to find values. It suffices to find these values so that these L's are very small. But note that here the policy has disappeared. We are just looking for values. We don't care about policies anymore. We just need to find these Q's. So now we can forget about actually finding a policy, but now we just want to learn a map Q from state action pairs to R, such that these L's, these errors, are as small as possible. If we manage to do that, then we construct the deterministic greedy policy with respect to this map Q. The deterministic greedy policy is the following: is this one, which is defined in this way. It's denoted by Q, and to state S, pi Q assigns the action with the highest Q value. So it assigns the action A such that QSA has the highest value possible. It's called greedy because it just goes for at each state it chooses the action that maximizes the Q value. So if these L's are very small, close to 0, then the greedy policy with respect to Q is going to be very close to pi star. Why? Because this thing here, because pi star is the greedy policy with respect to its Q values. By what we saw, where is it? We didn't see. I didn't, by this. No, where is it? Yeah, sorry. So pi star, as we saw the other last week, is arc max of Q pi star of SA. So the optimal policy is just the greedy policy with respect to its Q values. If we manage to minimize these values to make them close to 0, then these Qs are very similar to the Q values of the optimal policy. So using the greedy policy with respect to this Q gives us a policy that is very close to this one. Okay, so if the model is known and the Markov decision process is finite and small, then these equations can be solved just by solving a system of linear equations, or if you don't have enough computing resources, you can use other methods such as dynamic programming. So if you know the model, meaning that we know rho and the map of rewards, and this is small enough, then we can solve this exactly and find the optimal policy. Okay, so this is how you would solve the reinforcement learning problem in this setting with these assumptions. But these are rather big assumptions. So as I said, it's assuming that we know how the model works, which is a big assumption, and that as an A, these sets are finite and not huge. So what happens when we don't have either of these assumptions? And there's a classic algorithm called Q-learning algorithm from 1992, which, as I understand, was a breakthrough, handles the removal of assumption 1. And then for assumption 2, there has been several works regarding environments where S and A are very big. But the most famous one, and probably the major advance in this regard, was done in 2013 by the DQN algorithm by Bellman, which handled problem 2 by using neural networks and gradient descent, as we will see later. So now I'm going to describe the Q-learning algorithm, and then I will describe the DQN. So DQN is very similar to Q-learning, but you have to replace something by a neural network and update state by a gradient descent step. Okay, so Q-learning. We assume we don't know how our model works. So now we cannot compute the expectation in these else. So that's why we cannot solve. We don't know rho, that's why we cannot solve this, because if we don't know it, if this is not known, then how do we compute this expectation? Okay, so what do? We put an agent that doesn't know anything, interact with the environment in order to sample information about it. So we just put an agent to try things, and then we keep record of what keeps happening. And this will allow us to approximate this rho. Basically, it allows us to sample from the rho. And if we can sample enough, then we can approximate its expectation. Okay, so the idea is that when at state S, the agent samples an action A from some policy it's following. It receives a reward R, and then the environment changes to state S prime according to rho. The agent stores this tuple in a so-called replay buffer D. So the replay buffer is just a data set where you store these tuples. The state you were in, the action you took, the reward you get, the new state you move to. Okay, and we will use the information stored in the reply buffer periodically in order to update our map queue. So we are all the time we are trying to minimize this. Okay, so first of all, this is the overall idea. Now I'm going to describe what policy the agent follows, and then how to do these updates. And this is basically the DQN algorithm once we solve these two questions. So what policy should the agent follow? In principle, it can be any policy, as long as it guarantees that all pairs, state action pairs, are visited as many times as needed if the process goes on for as long as needed. But people use the so-called epsilon greedy policy, which is defined in this form. So this would be epsilon greedy policy with respect to a map. And it is defined in this form. The action assigned to state S by this policy is either a random action with probability epsilon, or it just behaves like the greedy policy with probability 1 minus epsilon. Epsilon is about 0.1. Of course, you can tune this, but usually I give you values of this kind of parameters so you can get an idea of the magnitude they usually have. So with high probability, it's just greedy, and with some small probability, it's completely random. So this policy kind of makes sense. You need this part to make sure this condition. So you want to visit all pairs a lot of times. You need it to compute the correct QSA values at these pairs. But then, besides this, it makes sense that it is greedy, because our Q value is supposed to get closer and closer to the Q values of the optimal policy. So we are trying to learn the optimal policy, so it kind of makes sense that we choose a policy that kind of behaves like the optimal policy would behave if we had solved the problem. However, for Q learning, you actually just need to visit all states arbitrarily many times. That's the only true requirement. Okay, and I will just emphasize that this policy is used only during training. When you are done, you just use the greedy policy with respect to the Q function you found, but you don't want to have random actions when you are done training. Otherwise, you'll have some weird performance, and usually when you want to train so that when you are in a testing mode, you perform as well as possible. Okay, so how do we update the Q values as the agent interacts with the environment? Remember, the agent keeps interacting with the environment and keeps storing these tuples in this D. And then periodically we use D to update our Q values. Okay, take a tuple in the replay buffer and let us use this notation. Given a state X and some reward R, I write the Rx to denote R plus gamma and then the maximum Q value at state X. So ideally, we would replace QSA by the expected delta. However, but we don't have this expectation because we don't know rho again. So instead of this expectation, what we have is just a sample of these deltas. So instead of having the average delta, we have a sample of delta. So what we do, we just update QSA a little bit towards this delta. And how do we do this? We change QSA by QSA plus this value. So lambda is the learning rate, which is a very small number. And so if lambda was 1, then this update is just QSA becomes delta R S prime, which would be fine if this was actually the average value of delta according to induced by the distribution rho. But since we just have one sample, it might have nothing to do with the average. So we update it in this form with a very small lambda, so that the updates are not so dramatic. This is actually one way to incrementally perform averages. So I think it will be clearer in the next slide why this update is done in this form. So this is the update we do. The principle behind this update is that the average of n samples of a distribution tends to the expectation of the distribution as the number of samples grows. So if you make this update if you keep taking samples of delta and you make this update 1 over lambda times, then this is exactly the same as computing the average of 1 over lambda samples. Okay, so after making this update 1 over lambda times, your QSA will be the average of 1 over lambda samples. So if lambda is 0.01, it's 100 samples after 100 updates, you have the average of 100 samples, which you can think with some confidence that it is reasonably close to the true average, this true value in here. Okay, so this is the Q value update. So this process has theoretical convergence guarantees, and if the state space is not huge, then it is feasible in practice to apply it. Okay, so here is the overall algorithm for Q-learning. This way we see it from the beginning, and hopefully it just to review all the steps. So how does Q-learning work? You initialize an empty reply buffer T and a Q map Q as usual. The Q map is initialized randomly. And you let by Q epsilon be the epsilon greedy policy with respect to Q, and you let S be the initial state S0 of the environment. And then until you are satisfied or forever, you do the following. You sample an action using your epsilon greedy policy. Oops, sorry. Then you execute action A, you receive a reward R, and the state moves, the environment moves to state S prime. So then you store this information in your reply buffer. The state you were in, the action you took, the reward you receive, and the new state. Since the environment has moved to state S prime, you update S to S prime. S represents the current state you are in. If S prime is not final, otherwise you just start with the initial state all over again. This is kind of a technicality. And then at each step or every certain time of steps, it doesn't, well, you can choose, but either at each step or every 10 steps or whatever, you randomly select a mini batch B from the replay buffer, and you do the following. So this might be like 32 tuples from the buffer, or 256, or whatever, some number. And you do this. So for each tuple in the mini batch, you update the Q value. If the tuple is SA or S prime, you update the value QSA according to the update rule. Remember that this is delta R S prime. So it's the update rule we saw before. And when you are done with this update state, if your replay buffer has too many tuples, you remove the oldest in it. This way you make sure that tuples that come from very old Q values, which are no longer of good quality enough, are removed. So you want a reasonable amount of tuples to be stored, but you want to discard the ones that are too old because the information is not interesting for us anymore. Okay, so this is the whole Q-learning algorithm. It's the algorithm from 1992 I mentioned. So this is great, but there is just one problem, which is what happens if the number of states or actions is huge or it is infinite. If this happens, then to begin with, we might not even be able to store a value for each state action pair if S cross A is very, very big. Or we might be able to do it, but it might be so big that the pairs SA don't get visited often enough because there's so many pairs to visit that it takes forever to visit two pairs, the same pair two times. For example, you can think of chess, which has an estimate of 10 to the 120 board positions, which is a barbaric number. So what is a possible solution? Instead of computing a map, instead of computing the Q values of all state action pairs, you just choose some parametric map from the state action pairs to R. So you choose for example, you choose a deep neural network depending on some parameters that assigns a real number to each pair, state action pair. So now instead of finding all these values, one value for each state action pair, such that this is minimized, we just want to find a set of parameters such that this is minimized on average for the pairs SA. So this might reduce the number of values to compute dramatically. I think in AlphaZero uses neural networks. AlphaZero is based on a different algorithm, but it also uses neural networks, and it uses this kind of strategy to reduce the number of values you have to compute. And the neural network it uses has, I don't know, not more than 1 billion parameters. So it's going down from 10 to the 120 to 1 billion numbers, which is quite a reduction. Okay, so, but now we no longer want to update these values. We want to update the parameters alpha. So this step in here doesn't work for us anymore because now we want to change alpha, the parameters. So what do we do? So given a tuple in the replay buffer, we want to update the parameters so that Q alpha SA is closer to this thing here. So how do we do it? With gradient descent. I think no one should be surprised by now on this loss. This is just it's kind of the L loss I was using before. You just take the derivative of this loss in here with respect to alpha and update your parameters in the direction of steepest descent, which is a negative, the negative of the inverse of the, or negative of the gradient. And just a small note, because remember that in delta, alpha appears, but it appears inside a maximum, and maximum is not differentiable. So in this expression here, this delta is treated as a constant, even though there's an alpha. So the reason is because you cannot differentiate through the maximum function. And also, it doesn't really matter because even if we treat delta as a constant, making this update still moves Q alpha towards delta. So the DQN algorithm is just the previous Q-learning algorithm, but you use Q alpha and you replace the previous update state of the Q-learning algorithm by this one in here. There's some implementation aspects that you can change, but modulo efficiency and this type of things, it's just this. This is the DQN algorithm. It's the algorithm that was used. It was presented in that paper where they trained agents to play Atari video games. And just a word about that. So, as I said, DQN was originally used for training agents that play video games. The states were sequences of 4 consecutive video game frames. It's not just one frame because you put 4 in order to capture movement and movement direction and speed of objects. If you just have one frame, then you don't know if something is not moving or moving extremely fast. And Q alpha in that paper is a deep convolutional neural network. It's just a deep convolutional neural network. And it has 2 convolutional plus ReLU layers, followed by 2 linear plus ReLU layers, which is a relatively small network for nowadays. Okay. So this is the description of the DQN algorithm. And now I'll try to describe the AlphaZero algorithm. Let's see. Maybe I'll take 5 minutes extra. Hopefully that's fine. So recall that AlphaZero is an algorithm that is applied when the dynamics row and the reward map is known to the agent. So if you know row and the map, you have an advantage, which is that you can plan ahead before making an action, because you can think what your action, you can try to predict what your actions how your actions will affect the environment, because you can sample in your mind from this row. So a popular family of algorithms that does this is called Monte Carlo tree search. Historically, this has been developed for playing games, especially Go. Go used to be a big open problem in artificial intelligence, which was solved 3 years ago, unlike chess, which was solved decades ago with this deep blue and Garry Kasparov matches. And AlphaZero is a type of Monte Carlo tree search algorithm. And we are going to assume for the rest of the talk that row is deterministic for simplicity. Okay, so Monte Carlo search algorithm takes a state S as input and outputs a probability distribution, MCTS of S, over the set of actions A. So the algorithm is actually giving you a policy. To each state, it gives you a probability distribution over actions. To calculate the distribution assigned to a state, you do the following on a very high level. You create, and I will explain in detail how you do this later. So you create and iteratively update a tree T, which stores information about different execution paths of the game starting at S. We will see now. And then you compute your distribution from the information that is stored in this tree. The tree has labels, vertices have labels in the set of states, and the edges have labels in the set of actions. And for simplicity, we will identify vertices with their labels. So we look at the vertices as states. Okay, so more detail. How do you compute the probability distribution given a state? So you initialize, I will discuss the general scheme of Monte Carlo tree search, and then I will explain how AlphaZero makes certain choices that I will leave open in the following explanation. So the tree is initialized with a single vertex with a label S. And then you are going to perform a fixed number of simulations, which I will describe in the next slides. Each simulation consists of 4 steps: selection, expansion, evaluation, and update. And now I will explain each of these steps. So to compute MCTS, you perform these 4 steps a certain number of times. Each set of 4 steps is a simulation. Okay, so the selection step. Okay, don't read this yet. Look at the picture. You have yours. Don't look at this. This is from a different talk. Imagine you have your tree. When you begin, you just have one node. But imagine that you've done several simulations and somehow you have constructed you have some bigger tree. So you start at your initial state. This is S. The state you want to compute the probability distribution for the actions. And then you start selecting actions somehow. We will discuss how to select actions later. And you travel a path in your tree. So maybe at state S, you choose action A2. And then it moves to state S1. And then you choose action A1. And you move to S2, and so on. And you choose actions until you reach a leaf. This is a leaf, because there's no more childs in this node. So you follow this path and you end up with a sequence of state, action, until you reach a leaf vertex SF. So this is just, the selection step is just this. The following information is stored. You want to store the number of times a state S has been visited throughout all simulations, the number of times an action A has been taken at state S. You also want to store estimations of the value of a state S, which we will discuss later, and estimations of the value of picking action A at state S. So Q and V are not this Q and V are not the Q and V from the previous algorithms, but they play a similar role. So I will explain how to select actions later, and also I will talk about this Q and V later. Okay, expansion is very simple. You have made some selection, you have reached a final state, and now you simply add all possible childs of this state. So for each action, you add the resulting state of taking an action at the leaf node. So if you are here and you compute what happens if I take A1 at state S3, I move to this state. So you put this state in your tree. If I take action A2 at state S3, I move to a certain new state, which I put here as a node, and then I put a vertex, and so on. So you just expand the final state you traveled to in the previous step with one vertex for each action, and you put labels accordingly. S4, S4 prime, I don't know. You put the names. Okay, evaluation. So here, again, forget about these captions. It's from another talk. Here, you just assign a value, VSF, to the final vertex you reached in the selection step. So the way you do this depends on the algorithm. So the way you assign a value depends on the algorithm. In the original algorithm, in the original Monte Carlo tree search, here you just start taking actions randomly until you reach a final state. And then the final state of the environment. And then the value assigned to this state is the accumulated reward of the rest of actions, of these actions. Okay, and now you update the Q values so that the Q value of, we can look at state action pairs as edges. So the Q value of this would be S0, A2, is the average of all values in here. So it's equal to the average of V of this, the value of all the states we have below this one. Not these ones, not the ones put in the expansion, because we still haven't computed the value of these ones, just this. Okay, so here are the 4 steps. In the selection, you just choose a path in your tree somehow until you reach a leaf, not a final state of the environment, a leaf of the tree. Then you expand the leaf with the following possible states for each action. Then you assign a value to this leaf node, and then you update the state action values so that the state action values are the average of the node values below the edge. These 4 steps comprise a simulation, and you repeat them a fixed number of times per move. And once you've done this, the probability distribution over actions is the normalization of this vector. So remember that S is S0. So your probability distribution is, you just normalize this so that each number is, you divide by sum of NSA. And remember that NSA is the number of times that action A has been taken at state S during all simulations. Okay, so if A2 has been selected a lot of times during the simulations, then NSA2 will be one of the largest numbers in here. So A2 will be assigned one of the highest probabilities. MCTS, remember, this thing is a probability distribution over the set of actions. So the probability of choosing action A1 is the number of times we've chosen A1 during the simulations divided by the number of simulations. This is actually S, now that I think about it. So it's just this NSA divided by S, the probability distribution. And the number of simulations we allow, you can think of them as the amount of thinking the agent is allowed between moves. Because remember, the agent does this every time it has to make a move. Okay, so what steps are missing from what I explained? First, how you assign a value, how you assign values to states, and how to choose actions during the selection process. So what are the choices of AlphaZero? One, for the assignment of values, surprise, you use a neural network that goes from states to real values, and the value of a state is just the value given by the neural network. This means that we will have to train the neural network. And for 2, we use this formula here, which I think I will not explain. It is quite interesting. I could spend almost one talk discussing this formula and where it comes from, but it's fine. So this formula also uses a policy which is parametrized by a neural network. What is this formula saying? Basically, it's saying you have to choose the action that maximizes this thing. And what is this thing? This is the value of choosing action A at state S, which, remember, is the average of the values of the states below the edge SA. So this term in here is just telling you choose the action with the highest value. So here you are being greedy. And then this is a term that is made so that if there's some action that you have not taken too many times, then this state is going to favor this term in here will favor the action. Oh, I'm losing my voice. Sorry, I don't know what's happening. It's like I have something in the. Okay, let's see. Let's try. So this term in here is telling you choose the best action, and this term in here, if you think about it, is telling you choose the action that you have chosen the least at state S, and then you add them up, and they make an interplay. They balance choosing the best action and choosing some action that you haven't explored. Okay, so I'm not going to discuss more about this formula. It comes from, as I said, it's a very interesting topic. That it originates on a very simple problem, which has very little to do with what we are talking about now. Okay, I will skip this. And now, remember that we are using networks, neural networks, so we have to train them. Okay, I only have 2 slides, and I will be done. I don't know what's happening with my voice. So you start with, how do you train the networks? You start with random parameters, alpha and beta, and then you execute episodes where the agent plays against itself. Each action is selected using the policy MCTS. So for each action, you do all those simulations, constructing the tree, and so on. And you compute the probability distribution over the set of actions every time you have to take a state. Here in AlphaZero, the tree is preserved during the whole episode. Instead of deleting the tree after taking each action, you delete the tree at the end of the episode, but during the game, you can keep the tree. You keep the same tree and keep updating it in each simulation. Then for each episode, so each game is a set of states, actions. We store the following tuples. we store the tuple S0, A1, so initial position, first action, and R0. I will define R0 now, the R's now. So it's state, action, reward, and the reward should be 0. No, it's 1. Okay. So the reward of the Ri is 1 if so each state, so we just need this. Each state is a board position together with the information of whose turn it is to move. So states are just some arrangement of pieces on the board and then information of who has to move next, white or black. Okay, you need this because you want to assess the value of state, so you need to know who is to move at that point. So Ri is 1 if player P is to move and player P won. So it's 1 if, for example, at Si black is to move and black ended up winning the game. Or it is 1 if white is to move and white ended up winning the game. Otherwise, if black is to move and it ended up losing, Ri is -1. And similarly for white, and Ri is just 0 for all I if the game was drawn. So we start playing games. The agent starts playing games against itself and stores these triples. And when it has enough data, so these triples, it makes the following optimization of the parameters via gradient descent. So it wants the value neural network of, given a triple, it wants the value assigned to the state of the triple be close to the R. So B alpha is predicting whether the player that was to move at position S ended up winning, losing, or drawing. And then there is another term. So we also need to minimize this cross entropy, which means that we want to make the policy, the parameterized policy of the network, we want it to predict, so we want it to assign action A at state S. Remember that this A is very good because this was sampled from MCTS S, which is a very sophisticated, if you intuitively, it's a very good policy because it comes from computing all those, from doing all those simulations and storing that tree and so on. So it is a much better, this is a much better policy than pi beta. So if we are training pi beta to resemble this policy, we are making very big improvements on pi beta because this policy is expensive computationally. It comes from sophisticated computations. And by adding this optimization part, we are sort of storing all these computations in a neural network. Okay, so when you have made this optimization step, you empty your data set and you start all over again with the updated parameters. And you repeat the whole process for as long as possible. And last slide, as I said, the alpha learns the true final outcomes of board positions, and pi beta learns the very good predictions made by the Monte Carlo tree search algorithm. And once you have done this optimization, the next games you are going to play, you will have much better neural network predictions. And just a comment, final comment, this whole process is a form of so-called policy iteration, which roughly policy iteration is the following. So applied in this setting, policy iteration has the following form. So playing good episodes gives you ways, so you use good episodes to improve the value of the estimations made by your networks through the gradient descent. But being able to do good estimations and decisions allows you to improve the quality of the episodes when you use the networks during the simulations. So when you do simulations, you are improving on the networks. And when you do the gradient descent step, you are improving the networks with this improved, with the information obtained from the improved simulations. Okay, and this is all.
So is there any question for Albert? Or, if not, I think we should really thank him for this talk and the whole introduction class. Yes. So thank you very much.
Yeah, it was
very well done. Thank you.
Grazie. Thank you.
It was a pleasure. Hope you enjoyed it.
Well, I also think it's a good investment that you made. Very to explain it somewhere else. It's very nice.
Thank you. Okay, so take care, everybody. Hope to see you all soon.
Ciao.
Ciao.
Bye.
Bye.
Bye.